Hi everybody, in this recording we'll be going over section 3.3, increasing and decreasing functions and the first derivative test. Our goal is that by the end of this presentation you'll be able to determine intervals on which a function is increasing or decreasing, and that you'll be able to apply the first derivative test to find relative extrema of a function. First we need to know what it means for a function to be increasing or what it means for a function to be decreasing. So a function f is increasing on an interval when for any two numbers x1 and x2, in the interval x1 less than x2 implies that f of x1 is less than f of x2. A function f is decreasing on an interval when for any two numbers x1 and x2, in that same interval x1 is less than x2 implies that f of x1 is greater than f of x2. So basically a function is increasing when x moves to the right and its graph moves up. A function is decreasing when x moves to the right and its graph moves down. So in our graph in the far right, we see that the function is decreasing from the origin all the way to x is equal to a. Then it is constant from x is equal to a to x is equal to b. Then it is increasing from x is equal to b to the other endpoint of the interval. Now we will be introducing theorem 3.5, the test for increasing and decreasing functions. So we let f be a function that is continuous in the closed interval ab and differentiable on the open interval ab. If the derivative f prime of x is greater than 0 for all x in the open interval ab, then the function f is increasing on the closed interval ab. If the derivative f prime of x is less than 0 for all x in the open interval ab, then f is decreasing on the closed interval ab. Now lastly, if the derivative is equal to 0 for all x in the open interval ab, then the function f is constant on the closed interval ab. Here we're given the example where we're told to find the open interval on which the function f of x is equal to x cubed divided by 3 minus x is increasing or decreasing. So first we will differentiate the function, so we will take the derivative. So that means that f prime of x is equal to x squared minus 1 using the exponent rule. Next, we can determine the critical points by setting the derivative equal to 0. So x squared minus 1 is the difference of squares, so we can factor it into x minus 1 times x plus 1 and set each of those equal to 0, and we get that x is equal to 1 and x is equal to negative 1 for our critical points. Now since f of x is continuous on the entire interval, we can conclude that x is equal to positive 1 and x is equal to negative 1 are the only critical numbers. Lastly, we can make a table to summarize the testing of the three intervals determined by the critical points. So for x between negative infinity and negative 1, we test the value x is equal to negative 2. So f prime of negative 2 yields positive 3. So since 3 is greater than 0, then the function is increasing for x between negative infinity and negative 1. Now for x between negative 1 and positive 1, we can choose the value x is equal to 0. And f prime of 0 yields negative 1. So since negative 1 is less than 0, the function is decreasing on the interval negative 1, 1. And lastly, we will be testing for the interval 1 less than x less than infinity. So we will choose the constant x is equal to 2. Now f prime of 2 yields 3, and 3 is greater than 0. So that means that our function is increasing on the open interval 1 through infinity. So here are the guidelines that we just followed for finding the interval on which a function is increasing or decreasing. So first of all, we let f be a continuous function on the open interval ab. Now to find the open intervals on which that function f is increasing or decreasing, we first locate the critical numbers of f in the open interval ab and use these numbers to determine test intervals. Then we can determine the sign of our derivative f prime of x at one test value in each of the intervals. Lastly, we use theorem 3.5 to determine whether f is increasing or decreasing on each interval. These guidelines are also valid when the interval ab is replaced by an interval of the form negative infinity b, a to positive infinity, or negative infinity to positive infinity. Now we will be introducing the first derivative test, which is theorem 3.6, which states, let c be a critical number of a function f that is continuous on an open interval I containing c. If f is differentiable in the interval, except possibly at c, then f of c can be classified as follows. 1. If f prime of x changes from negative to positive at the point c, then f has a relative minimum at the point c, f of c. 2. If f prime of x changes from positive to negative at c, then f has a relative maximum at the point c, comma f of c. Now 3, if f prime of x is positive on both sides of c or negative on both sides of c, then f of c is neither a relative minimum nor a relative maximum. Here's an example of applying the first derivative test. So we're given the function f of x is equal to x minus 2 sine of x, and we're told to find the relative extrema in the open interval 0 to 2 pi, and we're also told to identify the interval on which f is increasing or decreasing. So the first step is to differentiate the function. So our original function f of x is equal to x minus 2 sine of x. So f prime of x, our derivative, is equal to 1 minus 2 cosine of x. Next, we find our critical numbers by setting our derivative equal to 0, and that happens when x is equal to pi over 3 and 5 pi over 3. So those are our critical numbers, and we can find those using the unit circle. Lastly, we construct our test intervals. So we will be doing 0 to pi over 3, then pi over 3 to 5 pi over 3, and lastly 5 pi over 3 to 2 pi, because our original interval that we were testing was from 0 to 2 pi. So for our first open interval for x between 0 and pi over 3, our test value chosen was x is equal to pi over 4. Now the derivative of that point is less than 0, so that means that our function is decreasing on the open interval 0 to pi over 3. Now for our next open interval, we have x is greater than pi over 3 and less than 5 pi over 3. So we choose the test value x is equal to pi, and our derivative at that point is greater than 0, so that means that our function is increasing. Now for our last test interval, we had 5 pi over 3 less than x and less than 2 pi, so we choose a test value x is equal to 7 pi over 4. Now the derivative at that point is less than 0, which means that our function is decreasing. So using the theorem 3.6, we see that we have a sign change at x is equal to pi over 3. So for x less than pi over 3, it is decreasing, and x greater than pi over 3, it is increasing. So that means we have a relative minimum. So the x-coordinate of our relative minimum is x is equal to pi over 3. Now to find the y-coordinate, we plug in pi over 3 into our original function. So f of pi over 3 is equal to pi over 3 minus the square root of 3, and that is our y-coordinate for our relative minimum. Now, we also have a relative maximum because once again we have a sign change at 5 pi over 3. On the left-hand side, it is increasing, and on the right-hand side, it is decreasing. So once again, our x-coordinate for our relative maximum occurs at 5 pi over 3. Now to find the y-coordinate of our relative maximum, we plug in 5 pi over 3 into our original function, and we get 5 pi over 3 plus the square root of 3 for our y-coordinate of our relative maximum. Here we're given another example of applying the first derivative test. We are told to find the relative extrema of f of x is equal to x squared plus 4 divided by 2x. So a little side note before we begin the process, the function f is not continuous because it is not defined when x is equal to 0. We see that if we plug in 0 into our original function, we will be dividing by 0, and that yields undefined. So first we differentiate the function, so the derivative of f of x is equal to x squared minus 4 divided by 2x squared, and that was using the quotient rule because we have a rational function. Next, we can find the critical numbers by setting our derivative equal to 0. And we get that x is equal to 0, x is equal to positive 2, and x is equal to negative 2. Now, x is equal to 0 is still a critical number because f of 0 does not exist. So we must also consider the values of x where f is not defined as critical points. So from our last slide, using our critical points, we were able to see that we had a relative maximum at the point negative 2, negative 2, and a relative minimum at the point 2, 2. But in order to confirm that without using a graph, we will once again construct our test intervals. So we had 3 critical points, so we will be having 4 test intervals. So the first one will be the open interval from negative infinity to negative 2. So we choose the test value x is equal to negative 3. We get that f prime of negative 3 is greater than 0, so that means our function is increasing on that interval. Our next test interval is the open interval from negative 2 to 0, so we choose the test value x is equal to negative 1. F prime of negative 1 is less than 0, so that means that our function is decreasing on that interval. Next, we have the open interval from 0 to 2, and we choose the test value x is equal to 1. F prime of 1 is less than 0, which implies that our function is decreasing on that open interval. Now lastly, we have the open interval 2 to infinity, so we will be testing at the value x is equal to 3. F prime of 3 is greater than 0, which means that our function is increasing on that interval. So once again, we see that we have a sign change at -2 and at +2, which confirms what we had just stated earlier, that we had a relative maximum at the point -2, x is equal to -2, and a relative minimum at the point x is equal to +2.